All right, so folks, we're going to get started on this beautiful Tuesday morning with 3.7, which is the derivatives of inverse functions. Okay, now what we know, that list continues to grow. We're looking at rates of change, both average and instantaneous. I feel like that's something that you folks have worked really hard to make sure that you understand conceptually, and that's excellent. I would make sure to brush up on that before Thursday's exam. We've talked about a bunch of rules, so many rules, in particular, all of these rules. Oh, internet, come on. Can you hear me okay, or is my voice lagging as well?
I hear you okay.
Okay. Well, let's try this again. All right, well, we've learned a bunch of rules. We did learn that chain rule, and we used that chain rule that we learned last week to actually talk about another rule. So the writing shows up, there we go. And looking at something called implicit differentiation. And just as a quick summary, can someone explain to me how we know when we need to use implicit differentiation? Like, what are some clues that we might look for in a problem if we're trying to find a derivative? Good. Now, I know some of you might find the discussions frustrating because I asked you to be really specific about your words, but one of the things that I feel like you're all doing much better now is when I'm asking questions, then you're answering them in the chat. A lot of these answers are so much more specific than they were like 2 weeks ago. All right, so I know it's not an easy process, but I love how you are stepping up to the challenge and really trying to be as specific as possible in those explanations. And so, for example, I see some really good thoughts like we can't isolate Y very easily, or we can't solve for Y very easily. Yeah, and it's that we have Y's that are kind of, it's not just that we see a Y in the equation, but the Y's are kind of mixed in together with all the other variables, okay? And so that might be something that we add to our definitions, is that Y's are mixed in with the other variables and functions and are also hard to isolate, all right? So we want to keep in mind that a lot of the equations we see are already Y equals. And so we don't necessarily think about that as, oh, we need to use implicit there, but secretly we've actually been using implicit the whole time. We've just already had the Y isolated, okay? Now today's topic, which I asked you to preview a little bit yesterday, is called, how do we find the derivative of inverse functions? And if you wouldn't mind giving me a little bit of feedback before we get started, if you could type a 1, and again, you can send this to me privately, but type a 1 in if you thought that based off of yesterday's Desmos activity, you felt really good about the content, or a 0 if you're like, I did not understand that activity. Okay, so we got 2 choices today. We're going binary, 0 and 1. Okay. And if you could give me like one reason why you have that score, like what about that activity made it challenging? And again, you can send this to me privately. You do not need to send this to the entire group. And I'll give folks a few more minutes to type in their responses. I know it can be hard to express why something is challenging. And I'm going to write down a few of the things that I'm seeing from more than one person. Okay. So if you happen to see yours up here, know that you are in good company. There's at least one other person who feels the same way. All right, so it seems like these are sort of the top 3 concerns that folks overall had at the class, which is finding equations from graphs. The wording was confusing and not sure how to apply old knowledge to this activity. And I think those are some of those are intentional and some of those are not. So this is always really good feedback, but I think it's important to keep in mind that all the graphs that you've ever learned, like x squared, square root, that kind of stuff, that's not just from like pre-calc or the earlier classes you take, but we actually use a lot of these graphs as we sort of move higher and higher into math. And so I'm going to write down a list of some equations that would actually be really helpful to know the graphs of, okay? And that doesn't mean you need to know them immediately right now, but it means that it might be sort of something to add to your toolkit in terms of mathematics, especially if you're going to move into higher and higher math classes. Knowing the equations that are x squared, x cubed, knowing what those look like definitely are helpful. Square root of x, cube root of x, e to the x, natural log of x. These are a lot of the graphs that often get forgotten because they're all the way from pre-calculus, but they are ones that tend to come up quite a bit. And there's one more in here, 1 over x, that I think is worth knowing, okay? Now I know this was on a Desmos activity, and maybe it was hard for us to find the equations that go with the graph. What's one strategy we could have used in that moment when we're like, I don't know what the equation is? Because we have a lot of technology at our disposal. So what's one way we could have sort of tried to move past that? Like, I don't know what the equation in the graph is. How do we find that equation? Well, I think that's actually a really good idea, Luca, that I know this is a Desmos activity, but nothing says we can't open up another Desmos window and kind of plot the graph and see if that matches the pictures we're seeing. Okay, and so I just want to remind us that we can use Desmos, especially as we're trying to learn about, why is that not coming up yet? Especially as we're trying to learn new graphs, or maybe graphs that were like, oh, I knew those ones, but like it would be nice to see a picture of those again. You can go ahead and plot them on Desmos. Just open up another window. And in particular, you don't have to go to the student.desmos. You can just go to, not that, desmos.com, and you should be able to graph things. So it's a really nice graphing calculator. All right, and let me go ahead and drop the link in the chat. But if you go to this, you should be able to plot graphs and see if they match what is the picture that you're looking at, okay? Juan asked a really great question. Does the point slope form only work for linear graphs? And that is true. It only works for linear graphs, okay? So these kinds of questions I think are so important. Sometimes we learn things and we don't think like, when can I use them and when can I not, right? And so think about how well you were able to identify when you can use implicit differentiation. That would be a great way to frame a lot of what you learn in math, is like, how do I know when to use this and how do I know when not to use it, okay? The second point about wording being confusing, I think that this particular section can be really challenging in terms of the wording. I think calculus overall can be very challenging in terms of the wording. And so part of this is like, I want to make sure we keep exposing ourselves to areas that are hard for us so that we have that opportunity to grow, okay? And last but not least, not sure how to apply old knowledge to this activity. I think that's totally valid. I think a lot of us had math experiences where we learn like one chapter and then we move on and we never see it again. And then we learn another chapter and then we move on and we never see it again. And I think that tells a really disjoint story about math. And so I realize that I'm asking us to think in a different way, because I want us to see all the different connections between the pieces of what we're learning. Because I think when we can see that web that connects everything, it just makes everything a little bit stickier, okay? So I understand that I'm asking you to do things that are probably very unlike things you've seen in the past, but I ask you to just kind of keep stepping up to that challenge, okay? I did get some questions about the Desmos activity yesterday, and so I was able to hopefully help out some of those folks yesterday. But in looking at who's completed the activity and who hasn't, I realized there are also people who had questions that I didn't hear from. And if I didn't hear from you, it makes it really hard to support you, okay? Because I can't like read your mind and say, oh, I think so-and-so is having trouble, maybe I should reach out to that person, right? That just becomes you suffering in silence by yourself and being frustrated by yourself. So the more you can sort of let me into that world of your learning, the more I can support you around that, okay? So that's my Tuesday morning blurb, but we are going to dive into the notes for today, and let's see if things make a little bit more sense, okay? So after we've done this, let's kind of revisit that activity and see what that question was really asking and how we can unpack the language in that activity. So I hope my screen share is going to keep up. I think it will. Okay, so derivatives of inverse functions. If you go to any textbook, you'll see something like this, okay? They'll give you a theorem, they'll give you a formula, and this one in particular has a bazillion words, a lot of symbols, and it can be very, very overwhelming, okay? So that being said, let's embrace that overwhelmingness, because it's not even 7:30. So what else would we be doing except being better mathematicians? And so let's go ahead and read through the inverse function theorem. Okay, so I'll give you a moment to read that on your own. It is on the screen. You could have your blank notes up as well. And what I'd like us to do, because I think it's so important before we start thinking about how much we don't know, I'd like us to put in the chat, what is one thing that we know about what's written here? It doesn't have to be the whole thing. What's one part of something that you're like, I know what that symbol means. This means find the derivative. Or I know what this symbol means. All right, so I'll give you a moment to read that over, and then let's start with things that make sense or things that you are able to translate from this theorem. Yes, I love this. I love this. Okay. So again, you can be completely overwhelmed. That's fine, but we don't want to get to the point of shutdown. We still want to be able to say, where can I find something that I understand? Okay. And so I love that the first two folks out of the gate are saying that this symbol, y equals f with a little -1 of x, is nothing more than the inverse of f of x, okay? Now, I really appreciate the next contribution here, which is that inverse functions undo each other. And I'm wondering, before we sort of leave that as like inverse functions undo each other, is there maybe some examples we can write down of inverse functions? So inverse function undo each other, right? And maybe let's write down, for example, can we think of some inverse functions? Oh, all right. Again, two very different, but both great examples, okay? So for some of us that are a little bit more mathematical, we might recall from pre-calculus that if you take a function and you have another function that you put inside of it, kind of like chain rule, then you switch the order, you'll actually end up with the same thing, okay? Now, this notation can be really intimidating for folks who maybe feel like, I'm really not that good at math. I don't understand all of that. So like, that seems too fancy for me, right? But I think we can root ourselves maybe in something, root ourselves in something a little bit more concrete, like if f of x equals x squared, what can I say is the inverse, right? So we'll use a little bit of that notation with the -1. The inverse is going to be, like Sophia said, the square root of x, okay? Now, in particular, if we think back to yesterday's activity, I think on slide 5, there was a pair of functions, a blue one and a red one. And some folks were like, I don't know what the equations are. Like, I know one of them, but I don't know the other one. And here's the thing, if one of the equations is x squared, and you know you're doing an activity about inverse functions, I bet you know what that other one is, okay? So meaning we do have that square root of x and x squared. Those are a pair of functions that undo each other, okay? I really like that next example as well. Sort of this idea that if you have like +3 and -3, we undo the +3 with a -3, right? And so those might be a variety of examples that we remember or we can think about, but I think it's important to say, okay, let me be patient with myself. What do I remember? What can I root all of this in so that I have something to build on, okay? Now I know there's something else in the chat about swapping X and Y's, okay? So one thing to keep in mind is that for inverse functions, you swap X and Y value. Okay, you swap X and Y values. Now, I bet if you had done a quick Google search about what are inverse functions, that you would have seen something about switching or swapping X and Y values, or maybe some of these examples over here. Okay, so that might be something else where you're looking at this activity and you're like, ooh, I don't remember some of this stuff. You can use Desmos to help you visualize things. You can do a little Google search to help you figure out what does that word actually mean, okay? And it doesn't mean you're gonna have to do that for all of the activities, but sometimes if we have a little bit more to patch in, we do have those resources at our disposal, okay? So let's see what we have here. Evelina, I see that you have put in some really good notation here that we have the derivative of the inverse. And so maybe we could say that, oops, this right here in all of its mathematical symbols really means the derivative of inverse. Okay, the derivative of the inverse. No, Desmos is not allowed on exams. Okay, so this is why I think it's really important as we move through the units to build that knowledge in, because exam day is you and your exam. Okay. All right. So we've got the derivative of the inverse. What does this mean? This symbol right here. The F with the -1 and a prime and an X. What does that mean? Ah, it also means derivative of the inverse, okay? Now I did get a really great question. That's not what I wanted to do. I did get a really great question yesterday about like, what do all these symbols mean? And I think it's important as you are seeing all these symbols to make sure you know which ones are the same, okay? Okay, I see a great question on the chat. Can we put graphs on our reference sheet? Absolutely. Okay, so when you're thinking about the exam, you also want to think, all right, what are some not only formulas that we've learned, but maybe there's some things from the past that I don't really remember that I should put on there. Okay, so I think that's really up to you. Everyone's reference sheet should be a little bit personalized for sure. I think it's actually harder to use someone else's because they may organize it in a way that's very different from how you would prefer to organize it. Okay. All right, so let's do one last thing. This, I think, is the challenging part. I'm wondering if we can unpack this last statement. 1 over that. What in the world does that mean? Ooh, okay. Got a lot of great ideas. Okay, so we have the 1 over, okay? So in general, 1 over something means the reciprocal of that something, okay? And I feel like that's such a small thing, and yet sometimes we forget that when we just have 1 over, that is another way of saying reciprocal, okay? So let's see, we've got some good things in here. The derivative of the inverse function. Okay, so let's start from here. The derivative of the inverse function is the inverse of the derivative of the original function. So where are you getting inverse of the derivative? Can I ask you to maybe explain that part a little bit more? Ah, okay. And see, this is where I think a lot of folks also have that same idea. Okay, that's why I wanted to ask that part. So 1 over something, okay? When we say reciprocal, we mean 1 over something, or we're flipping the top and bottom, okay? So let's actually, we have that 1 over something is the reciprocal of something. But maybe before we get to here, reciprocal means 1 over something, or you flip numerator and denominator. Okay, so a reciprocal means 1 over something, or you flip the numerator and denominator. Okay, an inverse means something different. An inverse means that you undo something. Okay, and so we typically think about inverses like plus minus. That's a pair of inverse functions. What's the inverse function of multiplication? Division, okay. The inverse of a square. Square root. All right, what about the inverse of a cube? Yeah, cube root. What about the inverse of sine? Ah, okay. I'm not asking for the reciprocal. 1 over sine would be the reciprocal. Oh, it's not cosine. It is sine with a -1. What's another way of writing that? Because depending on who you had or what textbook you had, there's actually another way to write this sign with the -1. Yes, arc sine. Yes. Okay. So this, I think, is actually a really, really important point. So when we have sine and we want to undo it, we're going to use inverse sine or sine with a -1 or arc sine. Okay. But if I ask you what the reciprocal of sine is, what's the reciprocal of sine? That is going to be cosecant, which is 1 over sine. Okay, so let's kind of pause here for a moment and let that sink into our brains, because I think that's actually really important distinction. And yes, Sophia's sign with the -1 is actually not 1 over sine. And I completely see where people would get that, right? The power of -1, we're like, oh, we move that to the bottom. But this symbol, the way we use it here, actually is the same as this symbol here, where we said the -1 means the inverse. Yeah. Okay. You can 100% find the inverse of sine. You can use your unit circle. So when you're finding the inverse of sine, you're actually finding the angles that go with the coordinate. Whereas when you're finding sine of something, you're looking for the coordinate that goes for the angle. Yeah, okay. So anyway, let's sort of get back to the point here. So the point here is that we want to be really careful about our language, okay? And so this is sort of continuing to build on that idea that when we say something, we actually have to make sure we're saying what we mean. And so if we go back to that earlier statement of, let me find it. So we had the derivative of the inverse function is the reciprocal of the derivative of the inverse function, okay? Now, this is a lot of words. And so I think what might be helpful is for us to try a couple examples. And let's think about how we apply these, and maybe that will help us clear up the pattern that I was hoping we could find from that activity, okay? One last thing that I want us to think about before we go, which is something that Luca said earlier, which is for inverse functions, you swap the x and y values. And when we think about an inverse function, I asked you to look at a lot of pictures yesterday. And so you would have the graph, right? You'd have your graph. And I don't remember, okay, I think that was red. There was one where you had this function. And what function do you think that is now that we've kind of talked a little bit about functions and their inverse? Any guesses as to what that equation was? Ah, okay, so this one we could say is y equals x squared, but only from the right half of it. Okay, so there is like another half to the parabola, but that wasn't part of the graph. And then the corresponding point, or the corresponding graph that we had, was this, a blue one. And what was that equation? Okay, so y equals square root of x, okay? Now, let's start with the red curve for a moment. And let's say I put 2 into this equation. What y value comes out? 4, okay. If I switch my x and y values, what will I get? Instead of 2 comma 4, what do I get? 4 comma 2. And turns out that point is on the graph of the inverse function, right? So if you drag the point along, you should have been able to see that the x and y values switched as you look at all of the points there, okay? And so that's one feature I want to make sure that we're aware of, is that especially on like slide number one, you should have been able to move some points around and kind of see what's happening there, okay? And so it's not that I want you to look at one picture and say, I drew one picture, you tell me what's happening. It's more that we want to be able to do things in a dynamic nature, okay? But one thing about these graphs that we might notice is this. What's so special about that line? Ah, what is that line, by the way? Okay, so y equals x is the line of symmetry for functions and their inverse function. Okay, so we have this line of symmetry, but what if I picked a point here? And let's say I told you that that point was 1.5. All right, I just gave you an x value. I didn't give you a y value, okay? Would you know the x value or the y value of that point on the inverse function? Yeah, you would know the y value, right? So if I give you an x value on the original function, you know the y value on the inverse function, right? What if I give you the x value on the inverse function? What do you know about the regular function? Good, good, good. Okay. So maybe let's write that down before we move on, that the x value on the inverse function, okay, the x value on the inverse function will be a y value on the original function. Okay, the x value on the inverse function will be the y value on the original. All right. Now I think this is actually going to be really valuable today as we do our practice problem. Okay. So let's do a couple problems. We've been talking a lot about concepts. And I think sometimes when we feel like we're not good at math, that is a very hard thing to engage in. So thank you so much for contributing to that conversation. But we're going to go through 4 questions that are very similar in flavor, okay? And so let's take a look at this first example, right? So we have, for each of these examples, I want you to find the derivative of the inverse function, okay? So if I were to write that out in words, I would say that this is saying, find the derivative of the inverse function find the derivative of the inverse function at what point am I looking for? Like, I don't want to find all the inverse functions, derivatives or the slopes, but I want to find it at a specific point, right? At x equals, or at, let's write a, okay? So I want to find the derivative of the inverse function at a. Now, is a an x value or a y value? Okay, so I want us to notice that a is an x value on the original function, on the inverse function. Where is it an x value of? How do we know that it's the x value on the OG function? How do we know that? So if we look at this, f with the -1, that means inverse function. And then they give us an x value. So it turns out that a is an x value on the inverse function. Okay, that's a really important point to take notice of. Okay, a is an x value on the inverse function. What does that mean it is on the OG function? Okay, that means a is a y value on the original function. Okay. So the symbols mean find the derivative of the inverse function at a. But we have to know that a is an x value on the inverse function, but that means that a is a y value on the original function. Okay. And that is exactly because of that -1. All right, so because we have that f to the -1, that tells us we're talking about the inverse function. Okay, so that's a great connection here. This -1 means that inverse function part. Okay, so let's try this question. Let's try number 1. All right, so example one says, here's your f of x. 3x cubed plus 4x squared plus 6x plus 5. Are they telling you about the inverse function or the original function? Okay. So this tells us about the original function, right? F of x, there's no -1, so it's not the inverse function. It's the original function. Okay, what does this a equals 5 mean? Okay, let's be a little bit more specific. I know that it means a equals 5, but yes, x value on f inverse is 5. And what does that mean? It means the y value on f is 5. All right, so let me pause here for a moment. Does this make sense to folks? They've given us the original function, but then they were very tricky. They gave us the x value on the inverse function. And then in our brains, we had to say, oh, you mean the y value on the original function. Is everyone okay with what we've written down here so far? The original function, the x value, the y value. Okay. All right. It is kind of tricky. That's why we're writing it out in words, okay? And we're not really using very many pronouns. Like we're not saying it is 5 or that is 5. We're being very specific. We're saying the x value on f minus 1 is 5, which means that the y value on f is 5, okay? So we're going to start by saying this. We are going to find the x value on f of x that goes with a equals 5. Okay, so that's going to be our starting point. We are going to find the x value on f of x that goes with a equals 5. With this equation, where do I plug 5 in? Okay, so since we have the x value on the inverse, that means that is the y value on the original. So I'm going to take this 5 and I'm going to put it in for f of x. Not for x, but in for the y value part. And so we'll get 5 equals 3x cubed plus 4x squared plus 6x plus 5. So our a equals 5 went in for the y value. Okay. This part is a little hard to convince students of, but I want you to try some numbers in your head and tell me an x value that makes this statement true. Oh, x equals 0. Okay. So we just try some numbers. And my suggestion with this guess and check would be to try really nice numbers first. And what I mean by that is try numbers like 0, 1, or -1. Okay, so actually very similar to the numbers that I ask you regularly, like tell me 0, 1, or -1, how are you feeling, right? So we're going to use those same numbers and try those for our guess and check. Okay, I don't know why this step makes students so uncomfortable, but just try some nice numbers, 0, 1, -1. Okay, now that we found the x value that we're interested in, here's what we're going to do for step 2. So for step 2, what we're going to do is we are going to find f prime of the x value from step 1. Okay, so we're going to find the derivative, and then we're going to plug in the x value that we got from step 1. Okay. Now, am I asking you for the derivative here of the original function or the inverse function when I write f prime of an x value? Good. I'm asking you for the derivative of the original. Come on, internet. Okay. There's no -1 here for that f prime, so it's asking you about the original. Okay, so let's take our original function and we're going to be like, I'm going to find the derivative. And so we get 3 times 3 is 9x squared plus 8x plus 6. So you're going to have to find out that x value from step 1. Okay, now the questions that I will ask you will be nice ones where you can guess and check, and they will be nice number. Okay, so I won't ask you for ones where you guess and check and the numbers like pi or something, or like 2.79154. Okay, they'll be nice numbers. What do we get for f prime of 0 then? All right, we plug in 0, we get 6. All right, here's our last step, folks. We're going to find the reciprocal of the value from step 2. All right, what is that reciprocal? Okay. All right, so we can all take that reciprocal 1/6, but I wanted us to write 1 over f prime of 0 to help us remember that that is what we mean when we say reciprocal. All right, here's where we tie this all back to the formula. If I want to find the inverse function and the derivative of that inverse function. I know that's a lot of things in the exponent, but the -1 means the inverse. The prime means the derivative. So if I want to find the derivative of the inverse at 5, I'm going to do the reciprocal of the derivative at 0, and I get 1 over 6. This, my dears, is the final answer. Okay. So we were given the original function and then the x value on the inverse, and that wasn't very helpful. So we were like, well, if we want to answer the question, what we're going to have to do is find the x value on the original function. So we did a little guess and check. Then we said, let's find the derivative of the inverse function, or derivative of the original, and put in the number we found from part 1. And then we found the reciprocal of that, and that was our final answer. Okay. Let's try one more question, but this time we're going to focus on the first, second, and third step. Okay, so we'll talk about what all the symbols mean, but we're going to focus on sort of a step 1, step 2, step 3 situation. Okay, so f of x equals this tells you about the original or the inverse.
Original.
Good. And a equals 2 tells us about what?
Y value on f is 2.
Good. So we could say that f of x equals 2, or we could say the y value on f of x is 2. Okay, good, good. And it's the x value of the inverse. Good, good, good. Okay. So first step from before, we're going to find x value on the original. And so we're going to just set up the equation. We'll get 2 equals x cubed plus 3 sine x plus 2 cosine x. And this is when it is helpful to know our trig values, like our unit circle values. We're going to try plugging in numbers. Again, we're trying to plug in numbers that are 0, 1, or -1. Okay, that'll be the flavor of question that I ask you to sort of find. So let's try plugging in some values and see what we can plug in to get a y value of 2. Someone asked about, should you put graphs on your reference sheet? Yeah, I think it might also be helpful to put some of the unit circle on that reference sheet, right? Have it ready to go. All right, so let's try 0. So 2 equals 0 cubed plus 3 sine 0 plus 2 cosine 0. All right, sine of 0 goes to 0, cosine 0 goes to 1. Yes, indeed, an x value of 0 works just fine here. Good, good, good. All right, so we found our x value. Now we are going to find f prime of 0. Okay. When I say f prime of 0, does that mean I plug in 0 into my original equation and then take my derivative? No, right? That means I have to take the derivative first and then plug in my number. All right, so let's take that derivative, f prime of x. We got a little power rule, plus 3 cosine x minus 2 sine x. And now we're going to plug in 0. So 0 plus 3 minus 0 gives us 3. Okay. What's our last step here? We find that reciprocal. Okay. So the derivative of the inverse function at 2 is going to equal 1 over the derivative of the original at 0, or 1/3. Okay. All right. So before we take a break, let's reassess where we are. You can send this to the whole group, or you can send this directly to me. A 1 if it feels better than it did at 7 a.m. A 0 if it feels the same as 7 a.m. and a -1 if it feels worse than at 7 a.m. So let's take a break right now, okay? So it is 8:05 right now. Let's be back at 8:20 a.m. So we'll get a good 15 minutes in. Seems like overall we're doing better. We'll be able to come back and do 2 more examples like this, and then we'll take a look at some inverse trig stuff, okay? So we're gonna come back. I may try and reset my internet to see if that helps with things a little bit, but I'll see you back here in 15 minutes, okay? All right, so before break, we sort of broke down these question types into 3 steps where we find the x value on the original function, we find the derivative at that point on the original function, and then we take the reciprocal. All right, let's do 2 more questions where we follow that same pattern and then talk about how do we know whether that's going to be the steps that we need to take or not, okay? So let's start with example number 3, okay? So with this, we can see that we have an f of x, and this is going to be our original function, okay? And we also have this a equals 3, which is an x value on the inverse, but that means it's a y value on the original, okay? So that train of thought is something I want us to really connect in our heads, that if we have an x value on the inverse, that means we have a y value on the original, okay? Now, let's go ahead and follow these 3 steps, okay? So first, we're gonna find x value on, oops, on our f of x, right? And so this is where we take that a value, we plug it in for f of x, and we guess and check to find our x value. All right, so I'll give you a moment to guess and check, see what values you think this might be. And again, we're thinking about trying nice values first. I'm not trying to throw you for a loop and say, I hope you guess like 1.972154 or anything crazy like that. We just want to try and guess and check some nice numbers and see if we can make the 2 sides of the equation equal. All right, so 0 works again. Now, I just want to caution us that it's not always going to be 0, okay? So we should try 0 is a nice one to try first, but if that doesn't work, we could try 1, we could try -1, okay? And it turns out that if we plug in 0, we will get this term will go to 0, right? Because 0 squared is 0. And then tangent of 0 is also 0. All right, so those are some nice numbers to know. And in Calc 1, it's not too late to start building that group of nice numbers that you know. I think it feels like maybe by calculus we should know all of this, but if you don't yet, it's okay. You still have time to learn it, but that time starts to drop off very quickly when you get into Calc 2 and Calc 3, okay? All right, so now we're gonna find our first derivative of the original function at 0. And we're going to be really careful to find the derivative first and then plug in 0, okay? F prime of x. All right, let's get our brains working with some of these derivatives. What is the derivative of 3? That is going to be 0, okay, 0 plus the derivative of x squared. Good. Plus the derivative of tangent pi x over 2. Ooh, 2 answers that I was hoping for. This is good, this is good. All right, class, we've got 2 options available there. What are our thoughts? Secant squared of pi x over 2 or secant x over x squared times pi over 2? All right, we've got 1 vote for the first one. I think the second one. Everybody else is not sure, maybe. All right, folks, it turns out that neither of them are correct, okay? So I know that we're typing things in, but we need to be really thoughtful about, are we keeping everything the same? And what rule or rules might we need to find that derivative? Yeah, we're gonna need trig, but we're gonna need chain rule, okay? Now this is the kind of chain rule that tends to show up when we talk about chain rule, okay? And so we're gonna take the derivative of the outside first. We're gonna keep the inside the same. And then we have to multiply by the derivative of pi x over 2, which is just pi over 2, okay? Yeah, there we go, there we go. So a few things, we wanna make sure that the inside part does not change when we're using chain rule the first time. We wanna make sure we use chain rule. And then the third thing I wanna point out, this squared, we have to put it in between there, okay? No one is gonna be writing secant pi x over 2 squared, unless they mean square this and then secant it, okay? And so that is something that we have to say, this is what the convention is, so we have to keep that squared or whatever power it is in between those, okay? So we found our derivative, now we're gonna plug in 0. So I'm gonna get 0 plus 0 plus secant squared of 0 times pi over 2, okay? Yeah, all right. Now, this part, I do expect that we know how to evaluate that by hand, okay? And so we're gonna walk through the steps in terms of what that means, but that means that on an exam, I do want to see those steps, okay? No magical answers, because magical answers make me think you got them from somewhere else on the internet. And I know we're not doing that. So show me your thinking, convince me and yourself that you know what you're doing, okay? All right, secant. What's another way to write secant? All right, it is 1 over cosine, okay, 1 over cosine. Now secant squared means we have 1 over cosine of 0 squared. Okay, so secant squared of 0 is equivalent to 1 over cosine 0 squared. Yeah, sounds like we might need to review that trig a little bit, okay? So definitely take a look at that trig refresher on Paul's notes. I think I sent out the other day. He's got some good sort of charts and things like that, but we want to know all those functions. All right, and we're going to multiply that by pi over 2. And let's see, when we plug in everything, cosine of 0 is 1. So 1 squared is 1. So we end up with pi over 2. Okay. All right, last step here. We're going to go ahead and find that reciprocal. Okay, we're going to find that reciprocal. And so we're also going to write the other part. We are taking the derivative of the inverse function at what value? What value are we finding the derivative of the inverse function at? It's not 0. It's not pi over 2. Yeah, it's 3. This is where we started our question, right? We wanted to find the derivative of the inverse function at 3. And all that's going to be is the reciprocal 1 over the derivative of the original function at 0. That means it's going to be 1 over pi over 2, which is just going to be 2 over pi. Okay. Yeah, it's a lot of inverse and reciprocal. And if in our brains we're just saying flip this, flip that, then we're going to mix up what we're actually finding. Okay, so as you work through these problems, I would encourage you to be really careful about whether you mean inverse or whether you mean reciprocal. Okay. All right, well, let's try one more. And so in this case, we have an original function and we have the y value of that original function. Okay. Now, sometimes I hear students say, you know, I didn't do well on the test, and that's because it makes sense when we go over it in class, but it's hard to do on my own. And sometimes when I sort of ask a little more deeply how students are studying, it turns out that people are just reading this and not writing it on their own. And so sometimes when we don't make it clear for ourselves, again, sort of that muscle memory piece by writing things down and annotating it, we actually lose out on all these opportunities to study, okay? I know that writing is like, oh, it's math, why should I be writing all these words? But pretty much everyone who responded before break said once we broke it down into words, it was a lot easier to understand. So if you know that that makes your connection stronger, why wouldn't you do it for yourself, right? It's okay to take 30 seconds to write a little bit more here and there. But I think you'll find that you leave yourself better breadcrumbs, better notes to come back to when you're studying for a quiz or studying for a test, okay? All right. First step, find that x value on the original, okay? So what are we setting this square root equal to? Yeah, we're setting it equal to 30, okay? Now, I think that this one, we could definitely plug in some numbers, right? So take a moment, try and plug in some numbers. Again, we are guessing and checking to see what x values make this work. All right, some people are saying x equals 1. So let's see, 1 cubed is 1, plus 4 is 9, and the square root of 9 is 3. Yeah, absolutely. Okay. Now, if it was really hard for you to plug those in, one thing you could have done is say, let me square both sides. Right? If we square both sides, maybe this equation is a little easier for you to guess and check it. All right. And so either way, we should get x equals 1 to work. Now this right here, this idea of let me turn it into a form that's easier for my brain is such a key strategy that sometimes we see square roots and we just kind of shut down. We're just tired. We don't want to deal with the square root. So we're like, I just don't know. Right? But as soon as we get rid of it, we actually allow ourselves to say, okay, hold on, before we panic, we actually do know more than we think we do, right? I think that second equation is so much easier to plug into. Yep, and some people like to solve for the x. So either way, whatever you find works with your strengths, definitely embrace that, okay? All right, let's find our f prime of 3 or f prime of 1. Good, f prime of 1. And we're going to find that derivative first. And as I'm writing this down, what rule or rules are we thinking we're going to need to use? We're gonna need that chain rule, okay? That is the #1 rule I want us to look at a question like this and see, all right? More than anything, we are using the chain rule here. And so we're gonna have 1/2 times that square root, that is the derivative of the outside, times the derivative of the inside, 3x squared plus 4, okay? Now, I just want to be clear about something here. For some of us, we're at a point that we can jump right to this derivative, and that's great, okay? Without showing the power rule and bringing down the 1/2, blah, blah, blah. That is absolutely great, all right? If you feel like you're in a place to do that, then do that, okay? However, if you've been showing me a different level of work and then you skip right to this, you may not get credit for that because it's so different than all the work you showed me before, okay? So as you move into that exam on Thursday, more work is better. Magical work makes me question where you got that from, especially if you've missed a bunch of assignments or you've shown me in discussions that you're not really sure what's going on in class, okay? So we have to make sure that our work sort of aligns with itself and where we are. And no one place is better than the other. It's just we have to make sure we're being true to ourselves, that we actually understand what's going on, okay? All right, let's plug in our 1. Let's see what happens. So I have 3 times 1 is 3 plus 4 is 7 over 2. And square root of that is going to be 1 plus 4 plus 4. And so I will get 7/6 as that derivative. Okay. Last step, I do want us to practice writing this part. I don't want us to leave our answer just as the reciprocal. I want to make sure we know how to write out the first part as well. So I'm going to find the derivative of the inverse function at what point? Good, good, good. We're going to find the derivative of the inverse at 3. And that's going to be the same as the reciprocal of the derivative of the original at what value? At 1, good. 1/7/6. Another way to say that is, what is the reciprocal of 7/6? 6/7. Good, good. All right. And so that is our slope of the inverse function at a equals 3. Okay. So as you are going through the quiz or the exam, make sure that you are sort of showing these steps, explaining your thinking, like where did you get these values from? How do you know what that symbol means? Okay. And so an example of that might be if I say, what does a equal 3 mean? And you say a equals 3, that's not addressing the question, right? I mean, it's true, but I don't know that that answer brings any value to like helping you understand the problem. So if I say like, what does a equal 3 mean? And you say that's the y value on the original function, then that is a much stronger indication that you understand what we're doing, okay? On quizzes or tests, will we always get problems that work by guessing? For this class, yes. Okay, so for this class, yes, we're always going to be finding things that'll be relatively nice number. Okay, I cannot promise what other instructors do, but for this class, yes. What is the real world application of this? Okay, so a real world application of this might be that you're trying to find the rate of change of some function, right? That's what we're doing when we're finding derivatives. We're finding a rate of change. So it might be like, how quickly is inflation changing? So like, how much is your money worth? Or like, how quickly is the stock market changing? And so anytime we're looking at rates of change, okay, particularly with money or something like that, a lot of economists use this, we might have information about an original function. And it might be too difficult for us to get the inverse function equation. Kind of like how yesterday it was too hard to get y by itself, so we just found like a different way to solve the problem. This is similar in that it might be too hard for us to find the inverse function. So instead, we have these 3 steps that still help us find the rate of change we're looking for. Okay, so anything you can think of that involves rate of change, and you have a function, but you don't know what the inverse is, you could use it there. Okay. All right, so this we'll see in this class. If you take something called advanced calculus at some point, you will see this again, but in a much more abstract way, okay? What we're gonna do next though, in this next part of class, is we're gonna take a look at derivatives of inverse trig. Okay, so remember at the beginning we said inverse trig is different from reciprocal trig. And another way to write inverse sine of x is arc sine of x. And this is not the same as 1/sine x. Okay, so we are looking specifically at like the inverse sine. How do you find angles from coordinates? Okay. Well, one thing I also want to put out here is that for those of us looking to take Calc 2 for Math 151, you will start your curriculum in the fall with a lot of this inverse trig stuff. Okay, so I'll try and let you know which ones come up more often than not, so that you know these are the ones that I should memorize and these are the ones that I don't need to memorize as much. Okay, but you're going to be solving more complicated problems using these derivatives in Calc 2. All right. All right, so let's list some formulas out and let's see if some of the patterns that we learned from trig derivatives actually holds true. So the first one up is our derivative of inverse sine, and we're going to highlight that nice and bright in a yellow because that comes up a lot in Calc 2. Okay, you use that one a lot in Calc 2. And it turns out that the derivative of inverse sine is 1 over the square root of 1 minus x squared. Okay. So the derivative of inverse sine is 1 over square root of 1 minus x squared. Okay. Any guesses as to what the derivative for inverse cosine might be? Like, what was one pattern we noticed about derivatives of trig functions that started with the letter C? Yeah, that it was going to be negative, right? And so as gross as these derivatives might look, it turns out that the derivative of inverse cosine is just like inverse sine, except it's negative. So we can write negative 1 over square root of 1 minus x squared. Okay, so in other words, if you know the derivative of inverse sine, you know the derivative of inverse cosine. It's just the negative version. All right, the next one, derivative of inverse tangent, we're also going to highlight with a nice bright yellow because that one comes up a lot in Calc 2. Okay. I want us to know the formulas. I want us to know the derivatives, but inverse sine and inverse tangent, I promise you, you will see again in Calc 2. Okay. The other ones you might see, but you'll see them less frequently, right? And Abby, you were correct. The derivative of inverse tangent is 1 over 1 plus x squared. Okay. Well, knowing that, what are our guesses for the derivative of that inverse cotangent? Yeah, it's going to be negative of the tangent one, 1 over 1 plus x squared. Okay. So the inverse sine, the inverse tangent, you see a bunch. And if you know inverse sine, you know the inverse cosine. And if you know inverse tangent, you know inverse cotangent. Okay. The last two you do not see as often, but they do come up every once in a while. All right. And so the inverse secant is 1 over the absolute value of x times the square root of x squared minus 1. Okay, kind of a grosser looking formula. We don't see this one as much, but it does once in a while show up. Okay, now if you know this one, what do you think is going to be true about the derivative of inverse cosecant? Yeah, it's going to be your secant one, but negative. Right? So we have come up with so many different formulas. I would really encourage you to write those out on your reference sheet. All these formulas, maybe some graphs have been a suggestion, maybe the unit circle, some nice values on the unit circle. All right, so lots of things that we can potentially put on this reference sheet just to make it so that we can move through the exam more quickly. Not that we don't have it in our notes, but if we can have a one sheet reference of all the important things from the chapter, that might be really nice to have, okay? All right, so let's work through some examples. All right, so finding the derivative, okay? So let's start off with number 5. What rule or rules are we gonna need in order to find this derivative? Yes, we're gonna need chain rule, and we might note that we're gonna use inverse trig rules. Okay, but I love how quickly we identified that chain rule, because this x squared is a huge indicator that we are using chain rule. Okay, so f prime of x, all right, and again, I want to see us write this part. If all you did was say this equals, and then you start writing the derivative, you're telling me that the function equals the derivative, and that's not true. Okay, so we just have to be really careful about our notation and say, I am now finding the derivative. All right, what is our outside function here? It is not cosine. It's not the whole function either, just the outside part. There we go. So the outside part, not the derivative. I just want to know what is the outside function, okay? So the outside function is that inverse cosine, right? And now, after that, now that we're taking the derivative, we want to say negative 1 over. Did this one have a square root on the bottom or no? Yeah, it had a square root. And did the x come first or did the 1 come first? All right, so 1 minus something squared. What is that something?
X squared.
That is indeed our inside function. So we need to be really careful with our substitution here, that everywhere we see that inside function, we keep it as the inside function. And then we can say, now let's multiply by the derivative of x squared, which gives us 2x. Okay. If we pack this up into a single fraction, we'll get negative 2x over the square root of 1 minus x to the 4. And that is our derivative. Okay. I would say that this part right here, and I'll put some red stars around it, that substitution of that x squared is the #1 place that students make mistakes. I don't want to see that. I don't want you to make those mistakes, okay? So we want to make sure we substitute in, just like we did for everything else, we take the derivative of the outside, the inside function does not change, okay? All right, let's take a look at example 6. What rule or rules might we need? All right, we need a product rule. Where is that multiplication sign? I just want to be a little bit more specific. Where is that multiplication sign that tells us product rule? So good. that is where that multiplication sign is, okay? Where is there not a multiplication sign? Where might someone think there is a multiplication sign but be completely wrong?
Inverse sine x, maybe.
Yeah, some people might think that there is a multiplication sign in between that inverse sign and x, okay? So I just want to write here, no multiplication. All right. So let's set up our product rule and then see what other rules we might need, okay? So if I set up my product rule, u equals x squared, v equals inverse sine of x. All right, I know we know du is 2x. What do we know dv to be? Ooh, super close. How do we modify? Yeah, there we go. There we go. 1 over the square root of 1 minus x squared. Do we need chain rule here? Because that was suggested. Where do we need chain rule? Yeah, let's see. It looks like our inner function here is x. And so the derivative of x would be 1. Oh, okay, okay. So here's the deal, folks. Some people just write this and they're like, oh, inverse sine. That's 100% wrong, okay? If you don't have something that you are inverse signing, the expression is not complete. So we have to have some sort of input into our sin x. All right, but we could use chain rule if we changed our problem. How could we change this part of the question to make us use chain rule? If we think about like a discussion type question, how do we change the problem so that we force someone to use chain rule? Yeah, if we did this, inverse sine of x squared, now we have to do chain rule. Or we could do inverse sine of e to the x, and then we would have to use chain rule. But if we have just a regular x, we do not need to use chain rule. Okay. Does that make sense to folks why we do not need to use chain rule here? All right, well, let me know if you still have questions on that, all right? I know that notation is hard. Mathematicians have chosen to write things in a certain way, and it was sort of established so long ago. You may or may not agree with it, and so it is important to make sense of that notation, okay? So we're gonna find f prime of x, and we're gonna plug that into our product rule, and we will get x squared over the root of 1 minus x squared plus 2x inverse sine of x. All right. And so not a lot to simplify here. This would be absolutely fine to leave this way. All right, any questions on example 6? All right, well, let's go ahead and move on to example 7. This will be our last example for today. All right. All right, so if the position of a particle at time t is given by s of t, what does s of t stand for again? Yeah, it stands for position, right? Again, probably a really bad selection of what it stands for when whoever established that. What's another way that I could ask for position?
X of
Yeah,
t.
exactly. So you might see it as S of t or X of t, but either way, we're talking about position, okay? And so we have the position function defined by inverse tangent of 1 over t. And I want us to find the velocity of the particle at time t equals 0, okay? So how do we find velocity? Good, we're gonna say that velocity is the derivative of position, okay? That means we need to take the derivative of inverse tangent 1 over t. So we're gonna take the derivative. And if you write dx here, that would be wrong. Why would that be wrong?
We're integrating with respect to t, not x.
Yeah, we're taking a derivative with respect to t, not x, right? And so we're going to take the derivative of that inverse tangent 1 over t, right? Now, what rule or rules do we need? And I saw someone say chain rule here. What do we think? Do we agree? Do we disagree? Okay. So as you are studying, I think sometimes it is just as effective to ask yourself, what rule or rules do we need, as it is to sit and do a whole problem. But in this case, we might notice that that inside part is not just t, not just t. So we need chain rule. Okay. So Sophia, you are correct. We do need chain rule here. What could I put in place of this orange blob so that I would not use chain rule? Yeah, if I had just a regular t, I wouldn't need chain rule, okay? But because I have some other function there, I will need to use chain rule. So we're gonna take the derivative of the outside, and tangent, or inverse tangent, is gonna be 1 over, and then we're gonna have 1 plus something squared. What goes inside the parentheses? Good, 1 over t, right? So whatever was that orange blob or whatever you use for that inside function, that stays for your derivative of the inside or outside function. but then we have to find the derivative of the inside function. So what is the derivative of 1 over t? Very nice. So we have negative 1 over t squared. Where did people get that from? Because I might look at that and think the derivative is just 1. Okay. And so this would be another example of, I would expect to see that we know this 1 over t is the same as t to the minus 1. And when we take that derivative of t to the minus 1, we end up with negative t to the negative 2. And then we write it like negative 1 over t squared. Okay. So some of us, I think, would really benefit from taking the time to write out that pink part, all right? Just to say for sure, convince yourself, okay, I know where these come from. I'm not just looking at someone else's work and saying, I don't know, let me just write that down, okay? All right. We are not done with this problem though. We have one more thing to do. And what is that thing?
Plug in 1.
Yeah, now we're gonna plug in 1, okay? So v of 1 is gonna be 1 over 1 plus 1 over 1 squared times negative 1 over 1 squared. And we do a little bit of mental math here. 1 over 2 times negative 1 will leave us with negative 1/2. Okay. Now, let's say I had given you units in the problem, and let's say position was in meters and time was in seconds. Would it be correct if I put a unit of meters at the end of my answer? No, why not? Okay, so velocity is actually meters per second. So when we say meters per second, we are describing how quickly the position is changing, or we're describing velocity, okay? What if I wrote this and I said meters per second squared? What would I actually be telling you my answer means? Yeah, I would be telling you my answers are acceleration, right? So we want to make sure we have the appropriate units. So for velocity, we want to say meters per second. If we just said meters, we would be telling someone about position. And if we said meters per second squared, we would be telling someone about acceleration. Okay. So all of these small things are ways that we can really just tie together that concept. Like, what are we actually finding, right? Not just putting down any random units, but like understanding what we're finding, okay? All right, so folks, we are gonna stop the video right here.